Welcome to lecture 12, the Divergence Theorem. It's entitled Gauss's Law and the Notion of Divergence. So the first thing we want to do is figure out how to define divergence. And I just want to remind you that unlike the movie series Divergent, here we're looking at the mathematical concept called divergence. We're going to start with a way to define the divergence that stems from Gauss's law. I'm operating under the assumption that you've all seen Gauss's law in your electricity and magnetism class or in a multivariable class. Gauss's law says the integral of the electric field, the surface integral, so I take the electric field, I dot it into the normal vector, and I integrate that over the surface. That's equal to the charge enclosed divided by epsilon naught. And I can write that as 1 over epsilon naught, the integral over the volume that's enclosed by the surface, and the charge density that lies inside that surface, which we call rho of r. Now the way to get the concept of divergence, we have to look at a very small volume and just apply Gauss's law inside that small volume. But the key is the volume is going to be so small that we can approximate the charge density as being a constant inside the volume. So here I've drawn a rectangular volume. It's got some total volume that we're going to call delta V. It's got some surface, and there's 6 different pieces to the surface. I've labeled 2 of them with a delta S. And sitting in the center of that rectangular parallelepiped is the point XYZ. And that is where we're going to be evaluating the charge density. So what we have from Gauss's law is the integral over the surface of that little box of E of r dot n will equal the integral over the volume of that box of rho of xyz dv. But because rho is a constant when I evaluate it at exactly the point xyz, I can write that as delta v, the volume of the box, multiplied by rho of x, y, and z. And then if I divide both sides by delta v, what I see is rho of xyz is equal to 1 over delta v, the integral over the surface of E of r dot n ds. Now if I take the limit as the box gets smaller and smaller, because the left-hand side, the charge density, is well defined, that means the right-hand side must also be well defined. And we're going to call the right-hand side the divergence. At this point, it's just a definition. Whether or not that's something that we can easily calculate or is difficult to calculate, we're going to see on the next slide. But at the moment, this is simply a mathematical definition of something that has a limit, in the limit where the box goes to 0. And we're going to give it a name. We're going to call it divergence. All right, so now we get to the hard part. We got to figure out how to calculate this thing. So we essentially are going to start from that definition, and in order to do that, we have to do this surface integral over the different sides, and I'm going to just call the sides top, bottom, left, right, and front and back. So let's go ahead, roll up our sleeves, and get ready to calculate the surface integrals of this vector-valued function f. I'm calling it f now instead of e to make it more general. But we're essentially just doing the integral over the surface of f dot n, where n is the unit normal to the surface that points in an outward direction. So we got 6 cases to look at. So let's look at the first 2. We're going to look at the top and we're going to look at the bottom. If I focus on the top, you can see the normal vector to the top is the unit vector in the z direction. That's just what we would call k hat. And so when I take f dot k hat, it's going to just give me the z component of f. And on that top surface, I'm evaluating it along the points x, y, and z plus dz over 2. Now, I'm going to ignore the x and y dependence when I calculate the integral over that surface, and I'm going to just say that it's a constant, and I'm going to multiply it by dx dy. But I am taking into account the fact that there might be some variation of fz with z, so I'm going to write it as z plus dz over 2. You'll see in just a moment why that is an important thing to do and why it's okay for us to neglect the dx dy dependence in the first two components, but we cannot neglect it in the third component, okay? So please keep that in mind. In principle, I should have done an actual integral over the surface rather than just saying fz of xy z plus dz over 2 times dx dy. But it turns out for the thing that we're trying to evaluate, it's okay to make that approximation. What you're going to see is when we evaluate the bottom, which we're going to do next, which is exactly the same, except the normal is equal to minus k hat because it's pointing in the downward direction. And I'm evaluating the function at z minus dz over 2. You can see that now there's a minus sign in front of the fz. So when I add these two together, if I did not make that approximation where I shifted the component of the z to z plus dz over 2 for the top and z minus dz over 2 on the bottom, when I took the difference of those two, because of the minus sign, I would get 0. But now, because I'm not taking I shifted those arguments by a small amount, when I take the difference of those two, I'm going to get something that looks like the derivative. So that's the key, whereas for the x and the y components, I'm not taking differences with respect to that. So those can just be evaluated at the value that's at the center of the box. Okay, this is really the whole key subtle point about this entire calculation. It's really important you understand it. If not, rewind for about 30-40 seconds and listen to what I just said again, and then we're going to press on and we're going to now look at the front and the back. So for the front of the box, the unit vector is equal to minus j hat because the y direction is into the paper, into your computer screen. And so I'm going to get a minus fy, x of y minus dy over 2, and z, and then I have to multiply it by that area element. Now it's going to be dx dz that I'm multiplying by. And the back has a normal vector that's equal to j hat, and so it's going to equal fy of x y plus dy over 2z multiplied by dx dz. Now that we're getting comfortable and good at doing these, we can go and evaluate the left and right sides. On the left side, my unit vector is minus I hat. So I get minus fx x minus dx over 2 yz times dy dz. On the right, n hat is equal to I hat, and so I get fx of x plus dx over 2 yz times dy dz. All right, now it's time to add all 6 of these different pieces together. Got to take a deep breath. It's a lot of stuff to do. So we also have to remember the definition of the derivative, as I had said before. And what we find is when we add all of those together, I can factor out a volume element, dx, dy, dz. And from the left-right, I'm going to get the derivative of fx with respect to x. From the front-back, I'm going to get the derivative of fy with respect to y. And from the top-bottom, I'm going to get the derivative of fz with respect to z. And that object that you have there, the dx, dy, dz is what we would call dv, or we might call it delta v, but at this point I'm going to call it dv. And the object inside the parenthesis we're going to call del dot f. That would read the divergence of f. So this is the definition of what the divergence of f is. So what we do is we divide by the volume on both sides. That then gets back to what we used as our definition of divergence. And so del dot f, which is the divergence of f, is just dx by df, d by dx of fx plus d by dy of fy plus d by dz of fz. And that little sign, partial derivative sub x, is a shorthand for d by dx, which you can see in the line above. And then we often think of del as an operator as a vector, d by dx times I hat plus d by dy times j hat plus d by dz times k hat, or written as I've written it in terms of component form, d by dx, comma, d by dy, comma, d by dz. All right, good. We now have figured out what the divergence is, and we now want to put this together into evaluating what is called the divergence theorem. So what we have to do is we have to start with some volume V that has a closed surface S that surrounds it. And what we're going to do is we're going to take that volume and we're going to break it up into many small cubes. Each of those cubes has 6 edges, just like the cube we just evaluated, and we're going to assume that it's small enough that we can approximate the surface integrals and the volume integral over that cube, just as we had done on the previous slide. Now, if we look carefully at the surface integrals, what we see, because the cubes are going to fit right next to one another, when we look at the normals of adjacent cubes, all of the internal surface integrals are going to cancel, because I'm going to have a normal vector pointing in one direction for one cube, and it'll point in the opposite direction for the adjacent cube. And when I add the two together, those are going to cancel out. So what I'm left with is whatever contributions to the surface integral are coming from the outer surface, because there's nothing that will match up that will cancel out. So when I sum all of these results over the entire set of cubes, I'm going to get a surface integral that just goes over the outer surface of the volume. Now, on the other hand, if I look at the volume integrals that I get by summing all of the cubes, I just sum all of the cubes. There's no cancellations or anything like that. And so when we put all of that together, the surface integral over the entire surface, which I write as integral over s ds f dot n, can be written as a sum over I over all of the little cubes of the integral over each of those little cubes of ds f dot n. But because of what we just have worked out from the definition of divergence, each of those surface integrals is equal to an integral over the volume of the divergence of f. So I can write it as an integral over vi dv del dot f, or divergence of f. And then if I sum over all of I, I'm going to get an integral over the entire volume, so I can then write that as an integral over v dv, the divergence of f. And when we put that together, that's called the divergence theorem. What it says is the surface integral over the outer surface of f dotted into the normal unit vector is equal to the integral over the volume of the divergence of f. And now that you've seen the sort of microscopic way in which that comes about, and now you see how that gets summed together into a macroscopic object, I hope that you will feel comfortable about understanding exactly what this divergence theorem really means. Now, if you think carefully about this, or think a little bit outside of the box, this is very closely related to the fundamental theorem of calculus, because what it says we're doing is we're taking this object. You can think of f, if you like, as the antiderivative, because we're taking an integral of a del dot f. That's some kind of derivative of the f. It's not all possible derivatives. It's one particular combination of derivatives, because the d by dx of fx plus d by dy of fy plus d by dz of fz. But I'm integrating that thing, and so f is kind of like the antiderivative, and the surface integral is kind of like evaluating that antiderivative on the surface. And that's very similar to looking at f of b minus f of a, which is what we got from the fundamental theorem of calculus when we were evaluating a definite integral. So if you like, you can think of the divergence theorem as a generalization of the fundamental theorem of calculus into a three-dimensional integral. All right, let's take a look at an example that I think is a really neat example. It shows how you can calculate the volume of an object simply by doing an integral over the surface. And that kind of sounds counterintuitive, but it actually follows directly from this divergence theorem. What we have to do is we have to pick the right f in order to make this work. So we're going to pick the vector function f to be the vector r, which is just x times I hat plus y times j hat plus z times k hat. Now let's take the divergence of f. I'll get a dx by dx plus a dy by dy plus a dz by dz. Each of those derivatives is equal to 1. When I add them together, I get 3. So the divergence theorem, and I'm adding just a factor of 1/3 in front of the divergence theorem, tells me 1/3 of the surface integral of f dot n is equal to 1/3 the integral over the volume of the divergence of f, but the divergence of f is just equal to 3. So that's just equal to 3 over 3, the integral over the volume of dv, and that just equals the volume. So now I have this formula for the volume that is equal to 1/3 the integral over the surface of f dot n. Kind of looks like an odd thing. Let's take a look at an example of how we can calculate the volume by taking a surface integral. Let's look at a sphere. So for a sphere, the normal pointing in the outward direction is always in the radial direction. And if I take r dot a unit vector in the radial direction, I just get r, the scalar r. the magnitude of the vector r. And so 1/3 the integral over the surface of f dot n becomes 1/3 r cubed, because remember, when I integrate over the surface, my integration measure has an r squared in it. So I'll get an r cubed, and then I have the integral minus 1 to 1 d cos theta, integral 0 to 2 pi d phi, just like you've seen before. Now the integral over phi, easy to do, I get 2 pi. The integral over d cos theta, easy to do, I get a factor of 2. So the net is that I get 4 pi over 3 r cubed. Well, lo and behold, that actually is the volume of the sphere. So this crazy equation actually works. We can also check it out for a rectangular prism of dimensions a by b by c. Now we have to evaluate 1/3 of that surface integral. We'll start by looking at the left and the right sides. When I evaluate it on the right side, I will get whatever the y coordinate is on the right side, multiplied by the area of the rectangle, which is a times c. And then I have to subtract from that whatever the y is on the left-hand side, also multiplied by a times c, because the unit normal vectors point to the left and to the right, and one of them is positive, one of them is negative. Similarly, when I go for the back and the front, I will get x back minus x front times b times c, which is the area of that rectangle on the front and on the back. And for the top and the bottom, I will get z of the top minus z of the bottom times a times b. Now, of course, the difference in the y-coordinates between the right and left sides of the box is just equal to b. The difference of the x-coordinates between the back and the front is just equal to a. And the difference of the z-coordinates from the top and the bottom is just equal to c. And so what I find is this is equal to 1/3 of 3 times abc. And indeed, that just equals abc, which is the volume of the rectangular prism. So once again, we've shown that this formula actually works. All right, I'm going to end by talking about what does the divergence look like in cylindrical and spherical coordinates, because it is not d by dr plus d by d theta plus d by dz. That's not the way that you get the divergence in spherical coordinates. You have to actually work out very carefully what it is. So the first thing we need to do is we need to figure out what is our unit vector system that we're going to be using in cylindrical coordinates. Now, of course, we're going to take one of the unit vectors to be in the z direction, which will just be a k hat, the normal unit vector in the z direction. We're going to pick one unit vector to be in the radial direction. The radial direction, since it's restricted to the plane, is x times I hat plus y times j hat, divided by the square root of x squared plus y squared to make it a unit vector, and I can write that as x times I plus y times j over r. That's the unit vector in the r direction. And then we have to come up with an e theta, which is a unit vector that's perpendicular to ez and er. Now I can just take a cross product to get that, or I can simply construct it. If I construct y times I minus x times j divided by r, you can easily look and find that the dot product of that, e theta with er, is equal to 0. It's a unit vector, and it's also perpendicular to both z and r, so that will be our unit vector. And so those will define the components of f in the r, theta, and z direction. And then the divergence of f is 1 over r d by dr of r times fr plus 1 over r d by d theta of f theta plus dfz by dz. And so it's a little bit different than what you might have just naively written down if you thought you knew how to write down the divergence in cylindrical coordinates. Similarly, if we go to spherical coordinates, we now have to look once again at what are the unit vectors we're going to take. We're going to have a ER, which is in the radial direction. We're going to have an E theta, which is in the RZ plane. And we're going to have an E phi, which is ER cross E theta. So it'll be in a perpendicular vector to those two. Once again, ER is easy to construct. It's x times I hat plus y times j hat plus z times k hat divided by r. E theta, a little bit harder to construct, but if you're careful about it and you figure out I need to make it perpendicular to the ER, but in that particular RZ plane, you find that z times x I hat plus y j hat divided by r times the square root of x squared plus y squared minus the square root of x squared plus y squared over r times k. That is actually the vector E theta. And then E phi will be constructed by working out what ER cross E theta is. Now, if I use those as my unit vectors, and keep in mind that those unit vectors do change directions as theta and phi change. Those unit vectors are functions of theta and phi, just like in cylindrical coordinates. ER and E theta will change as the angle theta changes for the cylindrical coordinates. Now, the divergence in spherical coordinates is even more of a mess. The divergence of f is 1 over r squared d by dr of r squared fr, plus 1 over r sine theta d by d theta of sine theta f theta, plus 1 over r sine theta df phi by d phi. And so there's no simple way to kind of reason out why it has this form. It can be worked out by carefully working out the derivatives. I'm not going to do that for you in this particular lecture, but it is something that you should do at some point in your life. I believe we might be doing it a little bit later in the class. In any case, this is the situation for cylindrical and spherical coordinates. You want to be sure that you can use the formulas. I'm not going to ever test you to derive the formulas, but you need to know how to use the formulas, which means you need to know how to write a vector in terms of its r theta phi or its r theta z components, and you need to know how to actually calculate the divergence if you're given a function that has those particular components.